Welcome everybody. Let me first thank you all for coming either in person or remotely. I hope everybody is okay, as well as okay can be in those times. So we're very pleased that Nuno came to us this week, Nuno Loureiro from MIT, where he's the director of the Center for Fusion Science and Plasma Physics. Nuno did his PhD in Portugal, in Lisbon at the IST, and then spent postdoctoral appointments in Princeton at the Quantum Fusion Center, and then went back to Portugal to lead a research group before starting his position at MIT, where he is now. Nuno is a very, very accomplished scientist in plasma physics. He won the Thomas Dix Award for outstanding contributions as an early career plasma physicist. If you wonder what Nuno does mainly for a living, he solves a very, very good problem about magnetic recognition. The question is, how do magnetic fields dissipate energy? And then if you're interested in astrophysical plasmas, also how do you accelerate particles as well? So what actually makes many of the processes in the universe shine? Nuno has made really fundamental contributions to this decade-old problem, effectively finding a new instability, the plasma instability. But nowadays, if you look into any astrophysical simulation we do is ubiquitous. If you really work on the theory analytically, simulation-wise, he's worked on turbulence, on magnetic field generation near the universe. Is really a leading expert on the subject. And today, initially, as you saw one of the earlier announcements that you want to talk about this today, but then he came around, he was like, no, it's contact. Really, quantum is a big thing here. Many people are interested in quantum computation. So it's a second passion that he's been working on over the past few years about how can you actually leverage in the future, or even now, quantum computers or quantum computers, and how would you design algorithms to solve quantum physics problems that he's already worked on, this new and emerging technology. And that's what we'll talk about today. Thank you. So with that, take it away.
Appreciate it. Thank you, Elias. Wonderful introduction. Thank you, everybody, for being here. I understand these are times of stress for this community. I hope everybody's as okay as they can be. Thank you for showing up in person. So this talk is going to be much more aspirational than my usual talk. Elias said that my main research line is actually not this. And this says, I was telling John just 5 minutes ago, this is a recently acquired distraction, perhaps a midlife crisis or a post-tenure, I needed something different. So I started engaging in this topic, and I found it very intellectually rewarding and very interesting, even if results are scarce, as you're about to see. Okay, take this with a grain of salt and in more in the spirit of, entertainment than anything else. And it's, of course, very humbling to be giving a talk on quantum computing in this lecture hall with that person over there looking up at me. So I'll try my best, okay? So let me give you I'm going to try to give you some context for how these words actually got to be in the same slide: quantum computing and quantum physics and fusion. And once I've given you that context, I'm going to tell you a little bit about the efforts that my group has been developing around these directions and what the challenges are. The talk is sort of received for a broad audience. So I have some introductory material on quantum physics and the kinds of problems that we're trying to solve so that I can contextualize the challenge of quantum computing for plasmas. Okay? So for those of you in the audience who know more plasma physics than I do, I apologize in advance, but I felt like maybe some context would be good. So let me give you some context indeed. So things that are in the plasma physics sphere, one of them, of course, is fusion energy, which is these days in a stage of development and excitement that 5 years ago you couldn't even dream that you'd be here. There's been some very significant scientific and technological breakthroughs that have been sufficient to generate a whole private fusion industry, which is very vibrant and doing very well and promising interesting things. And of course, at the heart of considering fusion as an energy source is very difficult challenges in plasma physics. And so, of course, computation has played an enormous role in bringing us to where we are right now in the fusion sphere. I can talk forever about this. Another thing that is sort of in the classical physics sphere is this idea that you might have tabletop particle accelerators. So, very clever uses of lasers shining on different objects, you can generate electric fields that are incredibly high amplitude in spaces of a meter. And this has been explored as an opportunity for particle acceleration for multiple purposes. Space weather is becoming ever more important. So understanding the sun-Earth environment is a cosmic physics challenge. Understanding the solar wind, so right now it's actually a very exciting time as well for this area where you have the Doppler solar probe getting closest than ever to the sun and telling us all about the plasma that you find between here and the sun. So that's a very exciting time. And then, of course, astrophysics. There's a great number of problems in astrophysics that are, even though people sort of almost think that plasma is a dirty world in the astrophysics world, these are by nature plasma physics problems, magnetic field generation, magnification, cosmic ray, particle acceleration, Doppler emission jets. These are very difficult plasma physics problems. And again, at the heart of all of these problems is, very significant computational efforts that have brought us to where we are right now, but which, is still insufficient in terms of what you can do with a computer. And so, we're now, from a computational point of view, we're now at the bottom of the exascale era. And it's, of course, very, very exciting. People are excited about exascales and GPU architectures and all these things. But, it doesn't take very long to make the argument that even exascale puts you nowhere near to where you need to be to simulate realistic system sizes or realistic emissions parameters or anything like that. So, as you start thinking about quantum computing for some of these plasma problems, it's important to be aware of what it is that we're trying to solve and what is it to actually solve any of these problems. And so, in plasma physics, the kinds of problems that we worry about are various different dynamic problems, so time evolution of highly nonlinear systems. And turbulence is the typical example. It's ubiquitous, whether you're interested in fusion plasmas or astrophysical plasmas, you always have to contend with turbulence. And it's not just that the turbulence is there, it's the fact that turbulence actually decides the properties of your object. So everything that you're observing in that system is probably being regulated to some extent by turbulence. And so, what's the solution procedure? On a classical computer, you say, well, let there be this initial condition. I'm going to plug it into some set of nonlinear partial differential equations. I'm going to evolve this forward in time and see what I get, right? On a classical computer, you are all powerful. So you have the fields that you're interested in at every given point as a function of time. You have it all. It's great. You can do this. And, in some cases, you're only interested in the final state. So you're given an initial condition, and your only goal is to find out what is the final steady state. But in some other cases, no, you're actually interested in the path that the system took to get from A to B, as well as the final state. So, regardless of the application, this is represents enormous computational costs. Today's state-of-the-art simulations typically use tens of millions of CPU hours. This simulation you see here is not tens of millions. It's actually 200 million CPU hours. This is sort of the biggest simulation that's ever been done of magnetohydrodynamic turbulence. This took about a year and a half to run, and another year to data mine, and then write the paper. So this simulation here is, I think, the resolution of 64,000 squared by 10,000. So it's enormous, and basically there's only one. And this statement that was on one is probably going to remain true for the next 5 or so years, right? So we're at the stage where you can do one of these, and that's awesome, but you cannot do 10, right? And this is going to be true for quite some time. Right? And yes, there's enormous value in being able to do one of these simulations, but actually what you need to do is many of these because you're always interested in how things change depending on parameters. So one of these simulations, interesting as it is actually not enough. But then you might also ask, well, this simulation was 201 CPU hours. Is this simulation actually realistic? And the answer is no, it is not, right? So this is a fluid dynamics problem just with magnetic fields. You ask, what is the Reynolds number of the actual system you're trying to study? It depends, but it's going to be in the order of 10 to the 10 to 10 to the 18. What's the Reynolds number here? It's about 1 million. Right? So you pray to the Church of Asymptotology, you say, well, I can do 10 to the 15 Reynolds number, but I think 1 million is good enough. And that's what I can do. Right? And invariably, the story of plasma physics has been to discover that as you increase Reynolds numbers, interesting things happen that you didn't see at low Reynolds numbers. So there's a lot to be said for, where we are and where we need to be realistic in terms of the simulations that we can do. So one question that comes up very often is, so I'm a very unsophisticated plasma physicist in the following sense. Most of the plasma physics problems that I work with are classical, so they don't have any quantum effects, and they're not even relativistic. And so it's all classical physics. So Elias over there is much more sophisticated in terms of plasma physics that he does. He worries about special relativity, general relativity. And so, the question that comes up very often is, how hard can that be? Like, why is it that, you're not even worried about any 20th century physics, so to speak, right? And so, the idea to have in mind, I don't need to take you through these equations in great detail, but the idea to have in mind is, so think of fluid turbines, so Navier-Stokes. Couple that to Maxwell's equations, because in the plasma, you have electrons and you have charged particles, right? So their motion generates or changes the magnetic fields and electric fields that you impose. So to do the problem self-consistently, you have to couple to Maxwell's equations. Right? So remember, this is the set of equations that you're solving. It's a set of PDEs, the fluid parts coupled to Maxwell parts, right? And, the problem you know how to solve these equations numerically, but the problem is that you can't do simulations that are large enough to actually address the actual environments that you're interested in. So that's sort of the challenge. Even in neutral fluid dynamics, people are very far from doing the sort of simulations that are one-to-one to their systems. And in plasmas, you're much worse because it's just a harder computational problem. Great. Now, actually, if that's all that there was to this, you'd be kind of okay. But in fact, it gets much worse. So most of the problems that we're interested in, a large set of problems we're interested in, the plasmas are actually weakly collisional. That means that you can't assume that they behave as a fluid. The distribution functions are not Maxwellian, right? And so instead of doing fluid dynamics, you actually have to do a much more first principle thing. So you solve the Boltzmann equation for the distribution functions of your particle species, right? The electrons and protons, let's say. So what does that look like? It looks like a 6D equation that I wrote here. In plasmas, we tend to call this the Vlasov equation, but just think of Boltzmann equation. That's good enough for me. So you're solving the distribution function F, which is a 6D object, right? It depends on position, it depends on velocity. And then it develops as a function of time. And you have to couple that to Maxwell's equations for self-consistency. And so, if you thought that your computer was big enough to fit, let's say, 1,000 cube for a fluid dynamic simulation, if you now do 60 in terms of 3D, you quickly see that actually the biggest simulation you can do is probably on the order of 50 grid points to the sixth power. That's nothing, right? So a resolution of 50 grid points is pitiful, right? But that's about the best that you can do. So you deal with these things, and the parallelization is very hard. There's a lot of computational complexities associated with solving this equation. So it's just a hard thing to do, and so you have to rely on a lot of simplifications to be able to address any of the problems that surround us, from fusion to astrophysics, because those tend to be in collisionless regimes. So there's a huge scale separation in time scales and length scales in many of these problems. So this plot here, this is thinking more of the fusion plasma, but quantitatively this will map to astrophysical plasmas as well. So the vertical axis is the length scales involved in the problem, and the horizontal axis here is time scales involved in a problem. And so, for example, in a fusion plasma, you can have the radius can be on the order of a meter, but you have physics going down at least 4 orders of magnitude. And then in time scales, you can quickly span 8 orders of magnitude between the electron line in motion around the magnetic field, all the way to how the temperature profile evolves on a macroscopic scale, right? And so, quick analogy is easy. So imagine you're interested in predicting how the temperature in this room is going to evolve as a function of time, right? So, it might evolve on a time scale of hours, but actually the physics that's regulating that evolution evolves on time scales that are, that are 5, 6, 7 times smaller than that, right? So that integrating the system, and now you couple that with the fact that it's not actually this room, it's not actually air, like it's a collisionless system. So you're solving the Gaussian equation or the Boltzmann equation over, 10 to 7 time steps, with resolutions that would have to be at least 10 to the 4 in each direction. It's very, very challenging. So this simulation here is from a colleague of mine at MIT, Nathan Howard. It's now 10 years old, but at the time, this was 20 million CPU hours, and this was sort of the best simulation at that time of what turbines might look like in a subsection of a fusion device. And this is sort of groundbreaking because you see these big structures, and that's turbines at the ion scales. But if you pay close attention, you see that there's these very fine scale striations on this. And that's electron scale turbines. And so by virtue of doing this bigger than before simulation, Nathan was able to actually understand that turbines at electron scales and turbines at ion scales actually talk to each other and self-regulate. And so this was just an example of surprises that you'll encounter when you do a simulation that's bigger than what you could do before. So this brings us to 2018 and the context of quantum computing for plasmas and fusion. So back in 2017 or 2018, I can't remember anymore, the Department of Energy organized a series of workshops for all the sub-disciplines that are in their portfolio. So that included fusion, and so I attended. There's a report that comes from this. And so it was very interesting, and so this meeting combined experts from the quantum algorithm side with experts from the fusion side. And it had this sort of introduction where some DOE bigwigs said, fusion is very challenging computationally. You guys are always among the top 3 burners of computer time, in the best supercomputers that we have. Right? That's understandable, so it's a very challenging problem. So said, we're hearing that there's this nascent technology, quantum computation, and we're thinking, can this be used to accelerate the pace of discovery in fusion? And they said specifically, if we gave you fusion people a quantum computer, would you guys know what to do with it? And we said no. And they said, well, that's just as well, because we don't have one to give to you anyway, right? But they also said it was actually interestingly pressing to them. They said, instead of waiting 10 years for quantum computing to be a reality, and then start to think about algorithms, Should we start now so that 10 years from now, when they become a reality, we're actually ready to deploy and sort of move faster than we are? How much stock you're going to an argument like this? But, you know, during that meeting, I was intrigued by there was an obvious cultural clash between the fusion people and the quantum algorithms people, right? It was clear that, you know, there were interesting communication barriers about what it was, what the nature of the problem even was, and how you do this. So it's very interesting, that got me intrigued. And then, you know, there was being up to a grant proposal or whatever, and I got the grant to do this, and I started thinking about it. So that's the context to do this. So let's say, you know, when I say, you know, we're available to what it means for us today to solve something on a classical, what does it mean to say that you're going to solve it on a quantum computer? So I can do this, you know, with a very naive expectation that, you know, there is going to be some speed up, right? And so, you know, I quickly understood from my colleagues on the quantum side that factors of 2 or 3 are not very interesting at all. So we're talking about polynomial speedups or exponential speedups. That's the sort of thing that you want to do. And, you know, my understanding of this at the time was limited. And, you know, I understood that there were algorithms where there was demonstrably exponential speedup, so matrix inversion, perhaps. And that could be useful, right? But that's not enough because at the end of the day, you're trying to solve the problems, and that's very hard. But also, you know, the question of if you could solve these non-linear partial differential equations, what is it that you're actually going to measure that is interesting to you, right? So you're going to say, well, I can measure the solution at every grid point and get my velocity field as a function of position the same way that I do on a classical computer, right? That's probably not going to work. So how is it that I recast the problem or think in terms of different variables or something that will still allow me to extract useful information? So this, you know, maybe it doesn't make sense to think that the quantum computer is going to replace the classical computer, but can I recast my problem so that I can use the quantum computer to answer questions and solve the problem that I can't currently ask via the classical computation? So this is sort of an interesting paradigm shift, if you will. You know, I think it's wrong to think that you're just going to replace the classical unit with a quantum unit and be done. So another, so it's just for context. So these days, how do you develop any classical algorithm? Or how do you say, I have a classical algorithm, it's really good, it works faster for me. Well, what you do is you code it up, you run it, and you compare it to the previous run, you see that it's 3 times faster, and that's it, you're super happy. But, you know, you can't actually do this on a computer, right? You can't, the computers that exist are not actually powerful enough or big enough or error-corrected enough that you can just go ahead, try something, and see if it works for you, right? So it's an enormous burden on mathematical proof about, you know, is the quantum algorithm that we're devising actually exponentially faster? Can you prove this, right? And you have to prove this. It's a much more difficult step than actually implementing anything and, you know, just running it like you do on a classical computer. So from the application point of view, this is sort of delaying the progress that you can make because you just can't do this, right? So everything requires mathematical proofs that can oftentimes be very challenging. So this is, we partnered with IBM, so we went to see their headquarters, and this is one of their quantum computers. It doesn't do anything, it's just there. It's a beautiful thing that you can take a picture in front of. Okay. So, quantum is very efficient with some conditions like Hamiltonian simulation, something of this sort that you see here. There's a very famous problem in plasma physics. It's called Langdon. It's a linear problem. So what you do is you say, let me take class of equation, that I showed you before. So let me assume there is a pattern on the solution function. Let me perturb it. Let me study how that perturbation evolves. And you subject to an electric field, you find out the electric field will damp, and so that's called lambda system. Because you're linearizing this problem, you can show in actually two different ways that you can map this to sort of a Hamiltonian simulation. And so you can have a quantum algorithm that just does that. So you take this problem, you cast it as a Hamiltonian simulation, and because it's a Hamiltonian simulation with some conditions, you can show that for that particular problem, you can get a quadratic speed up. But you see, so this is the first example that I'm showing you. And you can already see how I'm thinking about this incorrectly. So what I've done immediately is I have, instead of saying, here's the problem I want to solve, let me find a quantum algorithm for it. What I did was the opposite. I said, I know what quantum algorithms kind of exist. Can I find a problem in plasma physics that would be amenable to something like that? So this is sort of backwards thinking. It shows that there are problems in plasma physics. Here's one for which you could get an advantage from a quantum computer. This is not a general problem. This is a very specific problem. In fact, a totally irrelevant problem because you can solve it analytically. So just showing that you can do this is a proof of principle of some principle, but actually not particularly useful. So let's look at many problems. So here's one. In this equation, so this is Berger equation. It's not an Navier-Stokes equation, but it's sort of, we talk about right nonlinearity, it has some viscous term. It kind of looks like many of the partial differential equations that we'd like to solve. Okay, simplified, it's just 1D whatnot. Now, for this particular equation, there is, it's known that there is a transformation, it's called a Kerr-Hopf transformation. And it maps that equation onto the heat equation. And now you're sort of happy because the heat equation is linear, right? So you can solve that equation with some sort of matrix inversion algorithm or something. And presumably that would be efficient on a quantum computer, were it not for the fact that the solution actually decays exponentially or polynomially as a function of time. And so you would have problems with amplitudes decaying, but in principle, this is a way to map a nonlinear problem to a linear problem, and that's great. Now, you still have to invert the Kerr-Hopf transformation to get the original equation, but let's say you can do that. So here's another example of something that's completely useless, right? And the reason is, yes, you can do this for this equation. But the Kerr-Hopf transformation only works for this equation, right? So if I give you a different PDE, you can no longer do Kerr-Hopf for it. Doesn't exist. This is a transformation that only works for this equation. So this is sort of a boutique solution to a boutique problem that nobody actually wants to solve. Okay. So again, an example of backwards thinking, like this is not one I want to solve. I just found a problem that can be solved, but that's not very interesting. This is more interesting. So this is a technique that's called Kalman linearization. So let me very quickly take you through this. So, consider an equation of this form. Okay. I'm going to use this equation as an example. You can actually do this for any linear equation. You say, let me define a new set of variables. I'm going to call them x sub n. They're just powers of x. And you take this and you plug it back in there, and you find the equation for x sub n is something like this. What you're now doing is you're treating the x sub n as independent variables. And if you think like that, you have mapped a nonlinear equation onto an infinite coupled set of linear equations. You haven't done anything untoward. This is not wrong. What you've done is you've projected a nonlinear problem onto an infinite space of linear problems. Okay? And this is exact. I didn't do any approximation. And As long as you keep an infinite number of equations, you're in good shape. These problems are exactly equivalent. Now, of course, we're not going to keep an infinite number. So you see that's how this variable, x of n, couples to the next one. And so you're inevitably going to have a truncation problem. Right? You're going to say, in my computer, I'm going to have 100 variables. So you need to decide what to do with variable 101. That's when you go non-numerous. That's when you say, actually, these two problems are no longer equivalent. The problem is that, in general, there is no small parameter here. You can't actually come up with a truncation based on the smallness of some parameter or some coefficient as you go to higher and higher volume. So you can't guarantee that the truncation converges or leads you to a problem that's actually equivalent to the original problem. And so we've done some work with this, with Andrew Child's group at the University of Maryland and Xinpeng Liu. So we applied it to this equation. Well, we did it in general, but then demonstrated with this equation. This is just a PDE that you discretize on a grid. And now you can do common variables on the values of your function at each grid point, and so on and so forth, right? And so this was actually, we could actually show that for this problem, common linearization does lead to a computational quantum advantage. But the problem is that convergence is only guaranteed if your nonlinearity is small. So in the case of a fluid example, convergence is only guaranteed if variable is number smaller than unity. Of course, what you want to do is variable numbers of I don't know, a million, right? So this is, it's interesting because it shows you that there is a way to solve problems that are weakly nonlinear. You can actually do this, but you don't have guarantees that they would converge if you make the nonlinearity much stronger. So this is just some results from that paper showing that things kind of work if you're in the regime where the ratio of the nonlinearity to the linearity is weak, or if the problem is dissipative enough. Here's another thing that can be done. So you take a Schrodinger equation with some potential, and you can do something called Lagrange transformation. And when you do that, you end up with a coupled set of equations like this, quantum hydrodynamic equations. And these equations actually similar to some fluid equations that you encounter in plasma physics. So there is a mapping in principle. These conversations quickly become about mappings, right? So the idea is, if I have a set of equations that I want to solve, can I find a mapping that takes them to sets of equations that are better on a quantum? And so the mapping transformation here is one such example. It doesn't quite work, right? So this thing actually requires, if this were a fluid, requires that fluids have no vorticity, which is very different than actual fluids. But it's an example of something that looks like a fluid set of equations, which we then coded up on computers are actually available on the web, the IBM quantum computers, and we could actually simulate something that looks like a shock. So this is a velocity as a function of position. So this would be a fluid that's coming in from the left, coming in from the right, and there's a shock front that forms here. So you're not actually solving the fluid equations, you're solving the Schrodinger equation with the right potential that then maps to the fluid equations. And the different symbols here are just different quantum computers that exist. And some are better than others, depending on the day of the week. That's not particularly important, but it's sort of a demonstration that you can do this using this technique of quantum walks that I don't necessarily want to get into. Another thing that we've thought about a little bit is this concept of lag spheres. And again, this is a sort of a transformation that works for some cases of exactly integrable nonlinear equations, like the KdV equation. Right? So, there's this transformation that will take the KdV equation and map it to something that's a coupled set of PDEs, and you can do very fancy things, something called inverse scattering transform, etc. And perhaps here you can have some sort of quantum advantage. But again, the only thing that I've told you so far that's actually completely general is the Kalman transformation, right? All these other methods are, it's in despair thinking, what mappings do I know that take a nonlinear PDE and map it to something that's linear or somehow more amenable to quantum computation? So, this is another example. This is actually a very interesting one and might be one of the very few problems that sort of almost straight out of the book sort of seems like inherently a quantum computing problem. So you take the NHT equations that I showed you earlier, magnetohydrodynamic, and you say, here's a plasma state, and I want to know if it's stable. In other words, if you were to kick it, will there be an instability that sort of grows? Now, to do this, you all have to do is linear theory. Okay, so you linearize those equations, and you try to see if the perturbation sort of grows. Okay. Now, these equations are very interesting because the force operator is remission, and so in principle, this satisfies all the conditions that you would have for a normal quantum mechanical problem. So it's like basically given a Hamiltonian, can you find its ground state, and from that you can say, does this thing have growing eigenvalues or not? So this is actually a legitimate fusion problem. This is actually something that you'd like to solve. We do solve this problem, on a routine basis. But if you could have a quantum advantage or do this much faster, then you can start to try different Plato configurations and try to optimize in that space much faster than you can do today. Right? So one of the things that people in the fusion business are playing with is this concept of a stellarator. A stellarator is a geometrically challenging device. It's a donut. But now you imagine that you section the donut in different octants, let's say, or more, and you twist each one of these octants by a different angle. And for reasons that we don't need to get into, this actually has very interesting confinement properties. But as soon as you introduce this degree of fusion that you can twist things, so you're no longer toroidally symmetric, you have this enormous optimization space, right? And you're trying to find the optimal configuration in that optimization space. And so you're able to run calculations, stability calculations very, very fast. Actually, it's a great advantage. It's something that you'll be very interested in. So we've been working on this with my graduate student at Amelie. Maybe it's going to be something published very soon. I'll just say the words. So Erica Yee was a postdoc, actually did a PhD here at Caltech in quantum chemistry, and then moved to MIT to work with me. She was an expert in something called tensor networks, and which come from quantum and simulation. And it turns out that you can use these same techniques to solve PDEs. And we started doing this thinking, maybe there's a quantum algorithm here. We still don't know the answer to that. But what we seem to have found is that these methods that are quantum inspired actually can have a classical effect. So for the cases that Erica tried, you actually be able to do faster calculations on a classical computer using these quantum inspired techniques. So this is sort of an interesting sort of parallel result here, which is you're looking at all these problems that you've been thinking about for 50 years in terms of classical computation, that you might be able to discover algorithms that you weren't looking at that accelerate classical computation if they don't do the quantum computation for you. Sorry. So this brings me to my summary. Plasma dynamics is intrinsically nonlinear, very strongly nonlinear. Nonlinearity is everything essentially. The reason we are where we are right now, in terms of understanding plasma physics and how plasmas behave, is largely through computation. So over the last 20 years, our understanding has rapidly matured because you can do simulations that you just couldn't do before. And so you're becoming very good at doing first principles calculations, but you're doing them, in regions of parameter space that are still very far from your actual applications. And so, we're trying to sort of overcome the computational barriers. And I was just talking to Elias earlier. If all we do is brute force, 20 years from now, we're going to be talking about a simulation that's maybe 3 times larger than what we can do today. But 3 times larger is nowhere near where you actually need to be to solve many of the ones that you want to look at. So I think it's not a controversial statement in plasma physics to say that force alone is actually not going to get you anywhere in our lifetime. So whether you buy into the possibility of quantum algorithms, or you think actually machine learning or AI or something else, right? But you have to think beyond brute force because that's not going to be sufficient. But we don't know how to solve nonlinear PDEs. And incidentally, I focus this talk on plasma physics because that's what I'm interested in. But the nature of the nonlinearity that we're dealing with is actually no different, at least in some cases, from the kinds of nonlinear PDEs that you'll find in many other fields of science and engineering. So it's not just about solving plasma physics problems, it's about solving pretty much any nonlinear PDE that you can think of. So what we've been doing is sort of rethinking how we sort of cast the problem. What is it that we actually want to measure? How are you going to go about solving anything? And if you could, what would you measure? Right? So it's very clear that this is sort of the field that requires collaboration. You have to have the plasma physicists and you have to have the quantum people, and it's sort of it's been very interesting and humbling to me to learn a little bit about this new field and sort of trying to understand how this can work. And so that's it. That's what I want to say. Thank you so much.
Thank you very much, Nuno, for a great and inspiring talk. Any questions?
You mentioned machine learning and guessing. What do you think are the best ones for biggest using?
So there's a large set of problems that people are applying machine learning to. If you're interested in control, plasma control, so you have an experiment, and your goal is not to understand anything at this point, you just want to make sure that things are behaving properly. Machine learning has actually made a lot of impact here. So there are now real-world demonstrations of machine learning algorithms, sophisticated neural networks that are monitoring the plasma in real time and controlling the plasma. So that's actually very useful from sort of a purely engineering point of view. But if you're actually trying to learn physics, that I'm not so certain about, because you can do things and you can accelerate solutions of equations, but you're doing this at the expense of the black box. And at the end of the day, it's not clear that you have learned anything, or that you trust it, or you can try that black box in regions of quantum space that you didn't already know about. So there's a lot of things that are going on there that seem interesting, but I'm yet to see an obvious application of machine learning that said, here's a physics result that I didn't know about, which I've been able to obtain because of this really clever machine learning.
Have you had that concern about falling algorithms as well?
Actually, no, I don't, right? Well, at least not in the way that I've been thinking about their potential, because you're still trying to solve the original problem. We're looking at these mappings, and you understand that the mapping is analytical, but there's actually an interesting recent trend going on, which is you can maybe use machine learning to discover the mappings themselves. So, so imagine that you are interested in a pendulum, and you wrote equations for the pendulum in Cartesian coordinates. And now you show it to the machine learning algorithm, and it's very clever. It tells you that actually there's a better representation, that there's an angle, and you can use it. You can use that instead of XY coordinates. And so, using techniques like this, you might be able to discover some of these mappings that you can't do analytically. Right? So there might be a mapping like that for some set of equations that I just don't know, but I can't write them. So there's a lot going on both fronts. People are in the machine learning business. One of the things that people are doing is they're constructing surrogate models that accelerate obtaining the solution. But once you have the solution, you can go back to the first principles and see if that's actually the solution. That's a clever way to do it. And so we're doing some of that in the fusion business.
As you described it, it sounded like the key was finding mappings between the classical problems and quantum algorithms. Is there a large inventory of algorithms that have been developed for quantum computers that you can kind of search through to try and find? Like in these cases, we've got a handful of problems that were well mapped to these. Is there a large inventory, or is that an area of a lot of development where people are just trying to write general purpose quantum computing algorithms to solve various differences?
My understanding is that no, there isn't a large inventory of quantum algorithms for which you can be certain that there is at least polynomial speed up with respect to classical. So, I mentioned matrix inversion, Fourier transforms, maybe, and these things are useful, but they are not enough, right? And I don't know of any quantum algorithm that allows you to deal with efficiently with nonlinearities. And so maybe I'm thinking about this wrong, and I'm, delighted to be corrected, but short of finding mappings, I'm not sure how you actually address this problem. And so the common thing that I showed you is the only general purpose mapping that I know. It's not tailor-made for a specific equation. But it's also very limited because it only works if nonlinearity is weak. But if nonlinearity is weak, I can solve it with pen and paper. I don't even need a computer, classical or quantum. So, yeah. So, I don't need for the statement to sound controversial. Right? That's, so if quantum computers are going to be useful for science and engineering at large, I'm not sure. You kind of think that you'd have to be able to solve many PDEs on them because that's what everybody does. That's what science and engineering is, right? So it feels to me like a very fundamental problem, not just from the plasma point of view, but from the point of view of science and engineering applications at large. Intrinsically non-quantum science, sure, you can do this for quantum chemistry and whatever. So forms that are by their nature quantum seem like an obvious fit, right? But a lot of forms that people deal with are not.
Let me ask a question. About finding those transformations. I wonder, doesn't it maybe just tell us we're looking at the wrong equations in the first place? Basically, what I'm asking is, I'm thinking it was the hydrodynamic example. Yes, thermodynamics. Maybe speaking, hydrodynamics is an effective field that you write down, but maybe the completion would be better. One particular example I can come up with is, for example, you can write down very nice astrodynamics and equations
that models the dynamics of a solid. Then you can melt the solid, the molten limit and recover hydrodynamics. So with the sugar neat completion. That theory has like a nice action, it has an origin, you can write that. Just wondering, like, if you're not knowing directly after the equation to solve now, but maybe about the related form, it's very similar. That just might be more relevant just in terms of the numerical form.
So, when I get into this, I thought exponential advantage, let's not underestimate what an exponential advantage means. Why do I have to be bothering with fluid equations? At the end of the day, I have an electron, I have protons. Let's just have them talk to each other and do an in-body simulation, right? F equals ma. Wonderful thing, right? So, because the problem is nonlinear, right? So I think even then, you're still struggling with the fact that you have to compute correctly the potential, the interacting potential of all these things. So, yes, you can go as first principles as you want, right? Yes, at the end of the day, you can treat the plasma as a quantum system, where the quantum effects are tiny. You could just do that, but I don't know that. Given the disparity in scales between what you're trying to do, right, and the description, I don't think that's the way. That's actually going to lead to anything computable. So yeah. So I don't. We don't have a better answer.
Paul. No. So, issue that occurred to me lately, and that you can have problems that are inherently complicated and that there's different things going on in different parts of the problem. So an example would be a battery connected to a light bulb. And so if you really want to do that right, you'd have to solve the chemistry of what's going on in the battery. You'd have to understand what's going on in the wires. You'd have to understand why the light bulb emits photons. And you like something that could solve all of that at once. Do you think any of these things could do that, or they provide an approach to the problem that has that degree of complexity?
Sorry, I'm not sure I understand the question.
Well, I mean, maybe solve problems now is we tend to look at the physics of each part of something, and then we connect it to other things by boundary conditions. Could you have something where you have very different things going on that are connected together and you don't?
So we do that, right? So in problems, as you know, many problems have very strong scale separation, and so turbine transport tends to be one. To have some time scale for profile evolution, but turbines is much faster. And so what we do is we actually hardwire that into the problem, and we have the equations for the turbines, we have the equations for the mean fields, and we couple them, correctly with transport coefficients. So that's already factored in. So I don't, this isn't about finding another decomposition. I mean, in plasma physics, we found we're very good at exploring asymptotics as much as we can, and sort of having, distinguishing physics that's going on at very different time scales and length scales as much as we can. But at the end of the day, we're still saddled with nonlinear degrees for each part of the problem.
I guess what I'm getting at is that what we're doing now is we know how to decompose it, but suppose you didn't know how to decompose it, you make something that's smart enough to do
That's right. So that not with what I've talked about before, but some of these, we are seeing now some machine learning techniques that are very good at recognizing certain symmetries of your system, or manifolds where solutions exist, and that I think has a lot of promise. So I've seen examples that are very special. So I don't know that this is a general purpose way of doing this, but this goes back to finding mappings or finding representations that are much more efficient of your system. So this is going on. I think we're going to see interesting action in that space for the next 5 years or so.
from the map itself.
Right, so if in the specific case of the specific case of column linearization, you're mapping something to a linear system, but it's an infinite linear system with infinite number of variables, right? It can have the same complexity as your original nonlinear system. In the case of Kohlhoff transformation, yes, you're mapping a nonlinear equation to a linear equation, but the mapping itself is nonlinear. So all of that is still contained in there, right? So there's nothing magical going on here, right? There's no, at the end of the day, you're paying the price one way or another. Like it's either via the transformation itself or via the fact that you're migrating to an infinite space or, something like that.
Also, the column vacancy depends on the condition and matrix. In these applications, there's when you need to do classical precondition. You use those elements and how does that affect the fidelity of the system?
Right. So the sad truth is exactly what you just said. So even in the cases where you can find mappings like this, you may in fact find that you're in with a very poorly conditioned matrix, whose set of eigenvalues is, spans a large range. And so in that case, you're probably inefficient. And so then what you can do is you can make some sort of approximations to the original equations so that the matrix that you end up with is better conditioned. Or you do some sort of preconditioning. So it's a case by case thing. In general, the kinds of things in general, plasma support many modes, and those modes can have very different frequencies or very different growth rates. So the general answer is going to be that the matrix is going to be poorly conditioned, unless you do something clever. So you're absolutely right. So even being able to recast it like that is in fact not enough. Yeah. So.
It's something that is some additional to take. Are there any issues with applying personality?
So it becomes a measuring problem, right? And so if you decide that you want to have, let's just step back, right? So right now, if I solve a problem on a classical computer, I have the entire time history of a field, velocity, as a function of position in my grid. If I say that this is exactly what I want out of my quantum computer, you would have to be not just exponentially efficient in the actual solving, but also exponentially efficient in the actual reading of the solution. And I don't think you're going to be able to do that. So I think you're going to have to compromise in you say, actually, I just want some sort of average property of, I don't need the solution at every grid point. I want to know the average, right? Or I want to know what the dominant Fourier mode of the solution is. Or you're going to have to, as a final step in your computation, you're going to have to take your final quantum state and represent it in a very efficient basis, of which, measuring two coefficients is actually very good. Like it gives you a very good idea of what your solution is. So you're going to have to be creative, not just about solving, but also about loading the problem, because you can have very complex initial conditions, which can be very inefficient to implement, and then reading the solution as well. So incidentally, this is one of the reasons, as I understand it, that hybrid algorithms, quantum classical, will be very challenging for a problem like this, right? Because you could say, well, so computers are good at inverting matrices, right? But they're not good at linearity. If I can do the linear part on a quantum computer and do the nonlinear part on the classical computer, and just do this, right? If you have a sort of hybrid architecture. Well, the reason is that every time step, you'd be reading and then reloading, so preparing the quantum state, reading it and doing it again and again and again, and this is very inefficient. So, right.